Alright, so we continue with orthogonal complements and orthogonal projections, and we just proved that if you're given a subspace V subspace, then V can be written or decomposed as a direct sum of this subspace and its orthogonal complement, which is equivalent to saying that every vector in this vector space can be written as a sum of a vector in U and a vector in the orthogonal complement, and this is unique. It's a unique decomposition. So here's the, using this you can define a map from V to U. Now define a map which is called projection onto this subspace from V to U, which takes a vector V, so this vector, and it maps it to this U. So for each vector you decompose it this way, and then you map this vector to this U. And of course it's a map from V to U. Okay, so this is called orthogonal projection. Onto U. Alright, so what are the properties of this orthogonal projection? We will see that essentially the problem that I stated at the beginning, namely this minimization problem with, let me just make sure that I ended in a reasonable amount of time this lecture. So, alright, so we have a map from V to U, and we want to understand what is the significance of this U. And it will turn out that this U is actually the vector in U which has the shortest distance to a given V. So that's kind of the solution of the problem that I stated. But before going into the formal properties of this map, let me go back to the example that I was considering, the simple example. U is z-axis and the complement is xy plane. Then if you take x, y, z, so what is the what do you get out of this particular definition? We have to remember that the orthogonal decomposition in this way, in this case, the decomposition into a vector from U and a vector from x, y, z plane is 0, 0, z plus x, y, 0, right? So this is my U and this is my W. So this map takes x, y, z and sends it to 0, 0, z. So this is a map from R3 to U, and in this case U is the z-axis, so you get a fairly simple map, right? You're forgetting the first two coordinates. That's this P for this case. Alright, so let me erase everything and start proving some of the properties of U. theorem. So for simplicity, I will denote by capital P this projection associated to a subspace U. Okay, so U is a subspace. U will be fixed. So we fix a subspace, and then we're looking at the orthogonal projection associated to U, and what are the properties? So the first property is that P is a linear map. All right. 2 is that the range of P is the whole U. And 3 is that the null space of P is the orthogonal complement. Okay? And then we also have this property 4, that if you apply P twice, then to any vector is the same as applying P to that vector just one time. So you get this strange equation between P iterated once and P itself. So once you keep iterating P, you don't get anything new. That's what it says. So if you apply P twice to a vector, is the same as applying P once. So you don't doesn't change the result. All right. So the proof of this is fairly straightforward, using the definition of P. And so let's see how it works. So if you take a 1, we're trying to prove that it's a linear map. So I have V1, which I decompose as U1 plus W1, and V2 I decompose as U2 W2. Then V1 plus V2 is obviously equal to this. Right, and because both U and the orthogonal complement are subspaces, so this is in U, this is in the orthogonal complement, so this is the orthogonal, this is the decomposition of V1 plus V2 into a vector in U and a vector in the orthogonal complement. So this means that P applied to V1, V2 is equal to U1 plus U2, simply from the definition of P. But then remember that P V1, again by definition, is U1, and P V2, again by definition, is U2, because it's the part that belongs to U. So this whole expression is simply P V1 plus P V2. And this shows that P is additive, so if you add two vectors, it's the same as applying P to each vector and adding the result. And then you can prove by a similar argument, it's even easier, that if you multiply V by a scalar, imagine you're multiplying by a scalar, then you multiply U by the same scalar and W by the same scalar, and then you apply P, you will get that scalar with U, and which shows that if you have a scalar here, it will come out of P, and that shows that P is a linear map. So that part I'll leave it to you to write the details. It's fairly easy. Now these 2 and 3 are again fairly straightforward. So remember that you can write every vector uniquely as a vector in U and a vector in the orthogonal complement. So this is here, this is in here, right? So PV is U. Now, obviously P is a map into U, right? And if you take any vector in U, then you get, right? So if U is in U, then what is this decomposition? It's U equal U plus 0. So PU is actually U. So you can get U as the image of U on the P. It's kind of a, I don't know, it's a simplistic way of looking at this, but we just showed, we exhibited at least one U that maps to a given vector in this subspace. So it means that the range of P is the whole U. So this is proved. Now, if you look at this, under what conditions PV is 0? Well, PV is 0 if this U is 0, right? So PV is 0 if and only if U is 0. And if U is 0, in that case, V equals W, and this belongs to the orthogonal complement. So this means that the null space is exactly the null space of P is exactly this orthogonal complement. So this is again check, and finally, again using this definition. Right, so PV is U. Now if I apply P twice to V, this is this P, PV, and PV is U, so this is PU. And then remember that if you have a vector in U, then PU is U, so you get U, which is the same as PV. So the square of P is equal to P. If you apply P twice, is the same as applying P once. And now, if you didn't follow the abstract argument, at least you should try to understand what this theorem says on that simple example that I've been carrying around throughout the lecture. So in the example, we have this R3 going to z-axis, right? So P x, y, z is 0, 0, z. Okay, and U was z-axis. So these are all elements of this form, 0, 0, z. Z is in R. And the orthogonal complement is x, y, 0. X, y are in R. Alright. So this is a linear map. That's clear because in terms of equations, all these coordinates are linear equations without constant terms. So this is a linear map. The range is U. Well, it's clear. If you take any particular specific value, you have many other triples with that number as the third coordinate. So that shows that there is at least one x, y, z that maps to this particular element in on the z-axis. Alright, so what's the null space? Well, which element goes to 0? The one that has 0 in the last coordinate. So the null space is the orthogonal complement. And then finally, if you project xyz to 0, 0, z, and then apply p once more, you don't do anything because you already put zeros in the first two coordinates, so you can replace zeros by zeros and you get the same vector back, right? So that's the argument. So p squared x, y, z is equal to p 0, 0, z, and this is 0, 0, z. Alright, so that's the proof of that property. And now we come to the important part, which is this, this problem that I mentioned. So this is the problem. Let V be a given vector, be a given vector in this vector space that we're working with, and U is a subspace. Right, so what we want, find a vector in U such that VU is as small as possible. Alright, and if you try to do this on a plane with the usual distance, so this is the norm of a vector, and which corresponds to the length in a usual Euclidean sense. So suppose we are trying to solve this problem in R2. Example. So suppose this is U, and then you pick some vector. So this is V. Now I want a point on this line such that the distance to V, to this point, is as small as possible, right? So if you pick a random point, then the distance will be this. And then if you pick this point, the distance will be this. And if you pick some point here, the distance is this distance. Now, if you ask anybody what the solution to this problem is, then they probably will come up with the correct solution, which is the shortest distance is actually this point, where this line is perpendicular or orthogonal to U. Okay, so this will be the shortest, the interval of shortest length among all these possible choices. Right? What is this point? Well, if you think about this for a second, what's the significance of this point? Well, the significance of this point is in the fact that it is the orthogonal projection, right? Because what is the orthogonal projection of V to U? what you want to do is to decompose V into a vector that is perpendicular to U, or orthogonal to U. So this is W, and then another vector that is in U, and so this is PV. Right, so the solution of this minimization problem, at least in R2 with the usual distance function, is the orthogonal projection. So we will show that this is true in general. So it's a very elegant solution to a fairly important problem. And then next time, when we will discuss how you actually compute this in practice. And we have a formula for this, but it involves having an orthogonal basis. So we will have to discuss how you find the orthogonal basis. That's sort of the important part that I'm leaving out for a lecture in the future. Okay, so here's the main theorem of today. Theorem. For any U in U, the distance between V and U is at least as large as the norm of V and the orthogonal projection of V into U. Right? So this is a vector in this U, and so this simply means that this PV is the closest point to V among all the points in U. So again, if, in a slightly more complicated example, if this is your V, and this is PV, and this is the point that is closest to V among all the points in U. So if this is U, then you obtain the solution to the minimization problem by taking the orthogonal projection. Okay, so let's prove this. So we can write V as PV plus W, and this W is in the orthogonal complement. So since U is in U and PV is in U, this U minus PV minus U is in the subspace. And because you have two vectors in the same space, so the difference will be in that subspace. Now, what we have is that this W, hence W, which is V minus PV, is orthogonal to PV minus U, since W is orthogonal to any vector in the space U. Alright? So now if you have two vectors that are orthogonal to each other, this this is a reminder of the Pythagorean theorem. If V1 is orthogonal to V2, then this V1 plus V2 squared is V1 squared plus V2 squared. And so we have this generalization of the Pythagorean theorem. And now we have two vectors that are orthogonal. So we will apply this to these two vectors. So we get that V minus PV, right, plus PV minus U squared is equal to V minus PV squared plus PV minus U squared. Okay, so we wanted to show that this element has the smallest norm among all other elements of U. So what is this expression? This expression, if you open the parentheses, you get V minus U is equal to V minus PV plus PV minus U. Okay, all right. So we want to show that this is at least as large as this, but a norm is positive, so this is a positive number, and so if we just ignore this, the expression will get only smaller. And that's the proof. So this is what we wanted to prove. So it's kind of hidden version of the Pythagorean theorem, and in fact that's what you're using, right? In this example where I said if it is in the plane, then the shortest distance is given by the orthogonal projection, you're really forming this right angle triangle where the usual Pythagorean theorem applies. So more or less what I'm trying to say is that the general proof is modeled on this observation. All right, and I want to conclude with an example of a calculation. Example. Well, let me draw a slightly more general picture. So if you're maybe working with a plane, and this is your V, that is V. This is PV, this is U, this is the subspace U, and this is your W. Right, and this guy, this dotted line, distance between PV and V. So we are minimizing this length. And now the example. Example, V is R4. So now we have slightly more complicated example where there is no picture necessarily with usual dot product. Let U be the subspace spanned by U1, which is 1 minus 2 minus 1, 2, and U2, which is minus 4, 1, 0, 3. Okay, so I have two vectors. They will span a plane in R4, and the inner product is the usual dot product. Find the closest point to V, which is 3 minus 1, 1, 13 in the subspace U. So that's the problem. You're given a subspace as a span of two vectors, and you're given this P. Well, we know the abstract solution of this problem. We know that this point that we're looking for is the orthogonal projection of D into U. The question is, how do you compute this thing? Okay. Fortunately, we're given a specific basis, which turns out to be an orthogonal basis. So first, we check that this is an orthogonal basis, and note that U1